Section 8.3, logarithmic functions as inverses. Our objectives are to write and evaluate logarithmic expressions. Logarithmic functions are the inverses of exponential functions, so that's really important. And remember, when we were talking about inverses, what do? You switch your x and your y values, just as a reminder. So that's a reminder. Now, for an exponential equation, remember that means we have to have a variable as an exponent. So exponential equations, remember this is your exponent. This is our base. And this is the answer. So if we look at the inverse of this, well, think about switching your x and your y values for something that has an exponent. How would we go about doing that? The only way that we can get the exponent down so that it's not there is by writing a logarithm. So the way that we write this is we write x is equal to the log base b of y. So notice that my answer is going to be the exponent. So this right here, notice, is your base again. And the base is going to be, you take the log, and it's a little number that goes next to the log. And that little number cannot be a negative number or 0. And we'll talk about why that is. This right here would be the answer from our exponential form, and this is your exponent. So again, we use logs to solve for an exponent because otherwise we can't just switch our x and our y's for this type of problem because it wouldn't be equal if we just did that, like when we did linear equations or quadratic equations. So note that the logarithm corresponds to the exponent. Please remember that a positive number raised to a power cannot equal a number less than or equal to 0. Therefore, a logarithm of a negative number or 0 is undefined. Now, some examples, like let's say I had y equals 2 to the third power. This would be exponential form. If I wanted to write this in logarithmic form, I would write the log. So notice my base right here is 2, so that becomes this little number right here. It's a sub number. And then we take this number right here, and that's going to become my answer. So this one is the log that we're taking of. So it would be the log base 2 of y is equal to 3. So let's do another problem. Let's say I had, and instead of writing y, I could have wrote 16. So if I wrote 8, so 8 equals 2 to the third power. So that's the same thing what we had over here. The log base 2 of 8 equals 3. And that's how we solve for our solutions. So for example, if I want to write the function 2 to the y equals x in logarithmic form, the relation would be written as log base 2 of x is equal to y. Notice that when you do inverse logarithm form, you are solving for the exponent. So again, that's an important part. Given the equation in one form, you can always rewrite it in the other form. So this is just written in words so that you can see exactly what you're doing. So for exponential form, you have a base and an exponent and your answer. To write it in logarithmic form, it goes log of the base of the answer is equal to the exponent. And remember, this number right here, the base, has to be greater than 0. You can't use 0 and you can't use negative numbers there. So just some examples that are already done for you. If we wanted to write 3 to the 4th power equals 1, 81 into logarithmic form, then you would remember that this is the exponential form. So logarithmic form, the base stays the base. So log base 3 of 81 would be equal to 4. So it's always equal to your exponent. For example 3, we have 5 squared equals 25. In logarithmic form, it would be log base 5 of 25 is equal to 2, which is your exponent. So let's do some examples. We want to change the following from exponential form to logarithmic form. So what I would do is pause the video and see if you can do these on your own, and then unpause it, and we'll do it together. So the first one in logarithmic form would be the log, the base is 10, so the log base 10 of 100 is equal to a value of 2. For the next one, this would be the log, and the base in this case was 2, so log base 2 of your answer equals the exponent. So the log base 2 of 8 would be equal to a value of 3. For the next one, the log, and the base in this case is x, so log base x of 16 is equal to my exponent, which is 2. And for the next one, this would be the log base 2 of 1 over 16, which I'm going to put in parentheses, is equal to my exponent, which is negative 4. So that's changing from exponential form to logarithmic form. So note, a common logarithm is a logarithm that uses base 10. You can write a common logarithm in two ways. We can write it as log base 10 of some number equals x, or you can write the log without the base of y equals x. So notice here the 10 is written, whereas over here we don't write it. So when the base is not written, it is of base 10. So anytime it's not written, it would be base 10. So like if I had the log of 7, this would be the same thing as the log base 10 of 7, just written. So one way we write it without the 10, in case you ever see that notation. So for examples, let's do the opposite of what we did before. We want to change the following from logarithmic form to exponential form. Now for this, if I want to go into exponential form, remember that the base becomes your base. So in this case, we have log base 2 of 32 equals 5. So remember that the answer is your exponent. So really, 2 to the 5th equals 32. It's easy to check your answer because in your calculator 2 to the 5th is equal to 32, so I know that's a correct exponential form. For the next one, we would write 5 to the 0 power equals 1, and that makes sense because anything to the 0 power is always equal to a value of 1. The next one would be base 10, because this is my base right here, so 10 to your answer, which is right here, is equal to 10. And anything to the first power is always equal to that number. And over here, my base is 1/2, so 1/2 to the first power, negative first power, not first, negative 1, would be equal to a value of 2, because remember when we have negative exponents, that changes it from the numerator to the denominator or denominator to numerator. So this would be really 1 to negative 1 over 2 to negative 1, so that would switch everything. So this would really be equal to a value of 2. So that one checks out. Now, why did I star examples F and G? The reason I starred them is because we have properties. This right here says the log base B of 1 is equal to 0. So that means the log of any base of 1 will always be equal to 0. For example, if I have the log base 17 of 1, I know my answer would be 0, because if I write this in exponential form, 17 to the 0 power is equal to 1. If I do another example, the log of base 100 of 1 would also be equal to 0, because if I write this in exponential form, 100 to the 0 power is equal to 1. So that will always be the case, so you need to know this right here. The next one says log base B of B is equal to 1. So the log of any base of the same number will always equal 1. For example, if I have the log base 5 of the number 5, that would be equal to 5. And you can also check by using the exponential form because 5 to the first power is equal to 5. If I had the log base 12 of 12, I know it's going to be equal to a value of 1. And the reason that is because 12 to the first power equals 12. So again, this is another property that you should know. Now that we know how to change from exponential form to logarithmic form and vice versa, you are ready to learn how to evaluate logarithmic expressions. To evaluate logarithms, it's helpful to use exponential form when you don't have a logarithm of base 10. If you need more examples of these problems, you can look on page 439 in your book. So I want to just show you really quick before we do some of these examples. If you go to your calculator, notice that there is a log button right here. If you hit that log button, notice it doesn't have a place for you to put your base. Because it doesn't have a place for you to put your base, that means your calculator can only compute logs of base 10. So what happens when we don't have a log of base 10? How do we solve these equations? Well, that's what we're going to have to do by hand. So like if I did this one, this would say the log base 10 of 8 would be equal to a value of 0.903, etc. And again, I don't have a button to put a different base, so we can only evaluate log base 10 in the calculator. So I'm going to write that down. Can only evaluate logs of base 10 in the calculator. So that means, what do we do when we don't have base 10, such as the next problem? So if I'm evaluating this, I'm trying to figure out what is the log of base 3 of 81 equal to? Well, how do I do this problem? I always like to think about it in exponential form. So the steps to do this would be put it in exponential form. So I'm going to write the steps over here. Put equation in exponential form. And then the second step is going to be get a common base. And the third step is going to be set the exponents equal to each other and solve. For example, so I have right now log base 3 of 81 equals something. I'm trying to find that something. So to solve this, since I can't put it into my calculator because I don't have base 3 in my calculator, I would do 3 to what power is equal to 81. Now, I would try to think to myself, well, I want to try to see if I can get the same base. So I need to figure out 3 to what power would give me 81 if I can do it. So if I do 3 to the second power, I know it's 9. 3 to the third power we know is equal to 27, just to show you. And let's try 3 to the fourth power. 3 to the fourth power is 81, so now I know I can get a common base of 3, since the base right here was 3. So if I do 3 to what power gives me 81, well, this would be the same thing as 3 to the fourth power. If I have something with the same base being equal, then I know, therefore, the exponents would have to be equal to each other. So now I can assume that x is equal to a value of 4. So I know that the log base 3 of 81 is equal to 4. And if you want to check your answer by putting it back in exponential form. 3 to the fourth power, is that equal to 81? And do it on your calculator. Yes, it is, so it checks out. So the next one, example 7, we want to evaluate log base 5 of 0.04. So this one, again, I'm going to set it equal to x and put it in exponential form. So 5 to what power is equal to 0.04? So now I want to see if I can get the same base. So I want to try to see if I can get base 5, since that's my base, because it has the exponential part attached to it. Now for this, I don't know what 0.04 is, so I'm going to, in my calculator, do 0.04, hit the math fraction key. When you do that, you end up with 5 to the x is equal to 1 over 25. Now that I have this, I recognize that 25 is the same thing as 5 squared. So really I have 5x equals 1 over, and I can change this to 5 squared because that doesn't change my equation. But notice that this part on the right is in your denominator and the one on the left is not. So I want to move this out of my denominator. How do I move something in my denominator? Remember, I changed the exponent so that it's negative. So 5 to the x power is equal to, if I do 5 to the negative 2, that's the same thing as 1 over 25. And now I have the same base. Since I have the same base, I can set the exponents equal to each other. So x would be equal to a value of negative 2. So that means that the log base 5 of 0.04 equals negative 2. And if I check, I know that 5 to the negative 2 power should be equal to 0.04. So you could always go to your calculator. So 5 to the negative 2 power, and notice I get 0.04. So it's an easy way to check your solution. So let's do another example. Oops. I have log base 1/2 of 8. So I want to figure out what that's equal to. So I'm going to set it equal to x and write it in exponential form. So 1/2, and I always like to put fractions in parentheses, to what power is equal to 8. So I want to see if I can get a same base. And 2 is the lowest number I can have. So I want to think to myself, well, how can I get 2 to what power would give me 8 so I can get a same base? Well, I know 2 to the 3rd power. So if I have 1/2 to the x, I know that's the same thing is equal to 8, the same thing is equal to 2 to the 3rd power. Now, if this part right here is written as a fraction, well, I don't want to have it like that. I want it to have the same base, and I want the base to be 2. So how can I make it so it's not 1/2? Well, isn't 2 to the negative 1 power the same thing as 1/2? And even if you're unsure, you can always plug it into your calculator. 2 to the negative 1 power, notice you get 1/2. So remember, it just changes the placement of where your number is when you add a negative exponent. So if it's in the denominator, it goes to the numerator to the denominator. So now that I have this, I can use my properties of exponents and just multiply the negative 1 times the x. Now that I have the same base, I can assume that if the bases are equal, that means the exponents have to be equal. So negative x is equal to 3, so x would be equal to negative 3. So that means that the log of base 1/2 of 8 is equal to negative 3. So if I want to check, I should be able to do 1/2 to the negative 3rd power, and that should be equal to 8. So you can always check again using your calculator. So 1/2 to the negative 3rd power, enter, notice I get 8. So let's do one more example. Example number 9. So for this example, again, same thing. The log of base 9 of 27 is equal to x. So I want to figure out what is that number. So write it in log or exponential form because it's in logarithmic form. So I would write 9 to what power is equal to 27. So I want to get a common base. Well, I can't, I can simplify 9 because remember 9 is really the same thing as 3 squared. And the reason I'm going to do that because I don't have a number, a base 9 that I can get 27 with. Because if I try to do 9 to the 2nd power, 9 to the 2nd power is equal to 81, and 9 to the 1st power is 9, which is not 27. So, but I know 3 can reach 27. So 9 is the same thing as 3 squared, so that didn't change my equation. So now I need to figure out, well, 3 to what power gives me 27? So in this case, if I did 3 to the 1st power is 3, 3 to the 2nd power is going to be 9, and 3 to the 3rd power, you should know by now, is equal to 27. So that's what I'm going to use. So 3 to the 3rd power. Now that I have the same base, I could rewrite this as 3 to the 2x power equals 3 to the 3rd. Since the bases are the same, I can go ahead and just set the exponents equal to each other. So 2x is equal to 3, so solve for x, and you get x is equal to 3/2. So if I write this out, I have the log base 9 of 27 is equal to 3 halves. So if we check, to check my work, I would do 9 to the 3 halves should be equal to 27. So let's go ahead and do that on our calculator to check. 9 to the parentheses 3 halves power. And when I do that, notice I get 27, so it checks out. So these are very easy to check your answers by, again, going back into exponential form after it's in logarithmic form, and then checking by plugging into your calculator. Now, we have the rest of these problems right here. So for the rest of them, you are going to try these examples on your own. Make sure you show your work, and then we'll go over them in class. So have these ready for class.